Is to go over the multiple choice on this. After we go over the multiple choice on this part 2, then we're going to quiz part 1, multiple choice. Okay, and then after we do that, you're going to work on the one free response question that you're going to have for homework. In fact, you'll probably have time in class. What I would recommend, you'll have 15 to 20 minutes in class left after your quiz. So I'll want you to use that time to do the free response question. All right, so here we go. Let's take a look. Okay, here you want to do your 5-number summary. You can actually do this by hand. If you put all the numbers in order, then you can find, you count them out, and the one that is in the middle, of course, is the median, the one that is in the center, and then the center of the bottom half is how you could count to the Q1, and the center of the top half is how you could count to the Q3. If you're in between two numbers, then you'd have to average them. But you could also, if you're not real confident on your ability to count, you could do one variable stats and put of list 1 and go down there and it'll do the 5-number summary. Okay? All right. This one here, straight up, just understanding the anatomy of a box plot and looking at the scale to the side. Number 3. Okay, understanding how to read a cumulative frequency plot. 20 percentile is this here, which is score of 96. 50th percentile is here, it's a score of 102, and then 80th percentile here, score of 106. I'm curious, I want to ask you a question. Where in this distribution are the steepest or the highest histogram bars? If I put a histogram together with this, where are the highest bars? The ones with the highest frequencies. Where? Yep. In this section where you have the steepest incline, that's because you have the quickest accumulation of data. So you would have, if you had histograms, you would have the highest bars here in the center, and then they get less, smaller accumulation there and small amounts of accumulation over there on the side. Okay, just think in terms of that. All right, here you're getting your correlation from R squared, but don't forget, R is the same sign as what? Slope. Okay, moving on. This one, you had to get the equation of the line, knowing that absences is the independent variable, and you're using those absences to predict your final. Okay, so that gave you that. Okay, this is a really, really good question to have a discussion on, so let's do that right now. Okay, so the question says, in this residual plot below, is this particular point right here, is that point an overestimate, underestimate, or neither? Well, all of these points that are on this actually occurred. This is an actual point, not an estimate. A point is not an estimate. What on that residual plot is an estimator? The line. This least squares regression line is the prediction line. That is what is estimating, or the dots are around that. The actual data is around that. So that's why this is a neither. It's kind of a trick question on that. Here's the way this question could have been worded to have given you an actual answer. This. Is the least squares regression line an overestimate or an underestimate of that particular point? So that's my question for you. Is the least squares regression line an overestimate or underestimate of that particular point? And what do you say? This is an underestimate of the point of what actually occurred. That is an underestimate of what actually occurred. All right, moving on. Okay, so on this picture, this is again your residual plot. So we can see there's a pattern in the residual plot. Therefore, the linear model is not really appropriate. So because of that, we know that the linear relationship is weak. It would have had a weak correlation, R value. And I'm sure that it would fit better. You would be able to find a better fit if you had done a transformation. Okay? Now, a lot of people ask me, what does this bivariate mean? What do you think that means? Two variables. So that's our x and our y variables. So it's asking you, basically, is the original graph of the x and the y negatively correlated? And the answer there is you don't know. Because from this residual plot, you cannot tell what the original was. The original could have looked like this, and then here I'm going to draw these dots around it. So I even drew like those particular dots. See, it could be that way, but it could also be this way. And then you have those dots arranged the same way around it. Okay, so you do not know if the original backtracking to is positive or negative correlated. All right, on this one, of course, I see all my answer choices over here, and so I'm thinking, ooh, well, first of all, we've never talked about that. I'm not even sure what interpolation is, so we're nixing that one. Okay, if I was to guess what an interpolation is, I would say it's inside the data. So if that would be my guess, is that interpolation is happening as a prediction inside the data there. Okay, but 2075 is not inside the data, because let's look at the years. What is the pattern that is happening on the years? The year doing what? Okay, the years are increasing. So as the years increase, what is happening to this time? What's the pattern that's going on with the time? Okay, the time is going down. All right, so based on that, first of all, upon using extrapolation, is extrapolation a good thing or a bad thing? Bad. So it is inappropriate. So I'm going to mark off the things that say inappropriate extrapolation. So we're left with, oh, that's wrong. I'm going to mark off the ones that say appropriate. My bad. Okay, just let's see here. Let's fix that. Extrapolation is bad, so we are marking off the ones that said appropriate extrapolation. Okay, sorry. Got ahead of myself. So now, what remains is inappropriate extrapolation, and we're wondering if the prediction is 9.19 or 9.91. Well, guess what? 9.91 is actually occurring in the data. So if this pattern continues, 9.19 is probably that one down there, is more reasonable estimate at 2075 if that pattern continues. So the answer is A. Okay? All right, next, here we go. This is some correlations things. 1 and 2 are true. We're going to go into why 1 is true a little late, more on another day. The reason 3 is false, it says R cannot be used to find the percent of variation that is explained. What is the percent of variation that is explained by the X or LSRL? R squared. And guess what you can do with R? You can make an R squared. So it says it cannot be used, and yeah, no, it can be used to find R squared. So there you go on that one. Okay, let's take a little look at this stuff. This has got quite a bit of good things to talk about here. This is 2 sets of data. One in which we were wondering if absences could predict the final exam grade, or absences could do the midterm grade. I guess exam, or I don't know if it's grade or final exam grade. All right, so the first question, so what I did was for both of those sets of data, I went ahead and did a linear regression. Okay, and so I did that, got the equation of the line, and then I got the R and R squared for those. Got the equation of the line, R and R squared. So for both sets of data, R and R squared. First question, are absences a better predictor of final or midterm? So what did I look at to determine that? R squared, your R and R squared, your correlation. So look at these correlations. These correlations are, this correlation is strong. This correlation is moderate. Okay, moderate or moderately strong. Okay, so yes, Absences is a better predictor of final grade upon linear being appropriate. Okay, I can tell I got this wrong at one point, but let's talk about number 2. Number 2 says the sum of the residuals is the same for both. So to have that little discussion, I've got a quick pick here. So here is your equation with some data points around it. What do we know about the positive residuals summed with the negative residuals? Haha, good. We know that the sum of residuals is always equal to 0. That means that's for both lines. So therefore, this set of data has a residual summing to 0, has the residual summing to 0, and this set of data has the residual summing to 0. So because of that, yes, they are the same. They are both 0. Okay. All right, how about this thing called unexplained variation? What is that? Unexplained variation. What have we always talked about? The explained. What is the explained variation? It can be explained by the changes in the x. So our r squared is the explained. How could I find out the part that is unexplained? Subtract from 100%. So here, in this case, 100% minus 92.4% means that 7.6%, if I'm subtracting right, then that's a big if, is unexplained. And over here, I've got 100% minus the 48.6%, which is 51.4%. And did I get those right? Somebody check me, see if I subtracted right, because I'll be proud of myself if I did. So, is the unexplained variation for final bigger than the midterm? That answer is no. Okay? Did I subtract right? Anybody checked it? Yay. Okay, good. Y'all don't want to subtract and figure it out either. All right, moving on. Okay, so look at here. Here, straight up, unexplained. 100%, take away the explained variation, and there you go, 12.9%. Now, FYI, big hint, I really like that problem we just did a moment ago, and this problem is almost identical to it, just with 2 different sets of data. So those are definitely quiz-worthy type questions. Hadn't made the quiz yet, but, you know, FYI, you want to make sure you understand these. This one is talking about points attempted predicting, used for a predictor of grade versus online activity attempting to predict your grade. So we have 2 sets of data. Of course, I'm interested in the r squared and the r. Okay, so here we go. Is points attempted a better predictor of the grade? So is points attempted or online activity better? Which one's better? Points attempted, because it's got a higher correlation. So points attempted is better. How about this? Sum of the residuals is the same for both. What is the sum of the residuals for both? 0. So, yes, that is correct. And the last one, unexplained variation. Okay, let's figure that out real quick. How much is this unexplained variation? 9.3%, and this one's like 70, is it 2.6 or something? I don't know, because I can't tell that number. And so does it say, which one does it say is bigger? Oh, that's wrong. It's 7, 6, I don't know. I can't subtract. I don't know what that is. Which one? It's way bunch different, so we don't have to worry about the nitty-gritties of it. Is this one unexplained is bigger for points attempted than online activity, and that's not right. Okay, so very same concepts. Moving on. Okay, this one really should be in part 7 of the review, because this really is having to do with a linear regression t-test and the assumptions. Okay, what are our assumptions that we did back in chapter 27 for a linear regression t-test? Line. Okay, and remember this I was also R. So guess what? That's why it is here. We want the sample to be randomly selected. That's this here. What does N, by the way, in our conditions stand for? normally distributed residuals. Okay, the residuals are somewhat normally distributed. Normal probability plot, so normal distribution of the residuals, and that's that. Okay, so there's that one. And E stands for equal variance in the residual plot. That is that one that looks like this, and you do not want it to fan out. You want it to be equally varied. Okay. By the way, that residuals are normally distributed. That's the, we were doing a histogram or that normal probability plot. All right, so there's that one. And looky here, here's an explained variation, r squared. Moving on. How about this one? How can you tell it is the best fit? Because it is the smallest sum of the squared residuals. Remember that game? Our thing I refer to, smallest sum of the squared residuals. Okay? And, okay, this one, first of all, my picture there is all messed up, and I want to actually have a couple points of discussion for this problem. So I'm going to save this one. I want to get some pictures together for you, and actually I have an app that I can show you some things real quick with. So this has several ideas in it I want to save for later. We'll spend some time on that another day, probably Monday. So let's move on to 17. What do you notice about that residual plot? It has a pattern. So what do you say about linear model? It's not appropriate. So the linear relationship is weak because a linear model is not really a good fit. It would fit better after you do a transformation, like exponential, power, or maybe even something else, quadratic. All right, bivariate, the original XY data is negatively correlated. Do you know what the original looks like? It could be going this direction, or it could be going this direction with the data around it. Okay? You don't know. All right. This one has no pattern in the residual plot, so a line does fit the data, and the linear relation is, well, I guess we're going to call it strong. Okay? And we do not know, again, what the original looks like, and if it's positively correlated or negatively correlated. We don't know. And here, again, this one you would find the equation of the line with absences are x and final exam is y. I do not like any of these equations because we know to interpret the slope, you say for every one increase in the days absent, the predicted grade goes down by 6.7%. So all of these are missing predicted, but since they're all missing predicted, I'll just pick the next best thing. Okay? Is that it on those? Now, after the quiz that you are going to take, you're going to do this. You will have a solid 20 minutes to work on this after the quiz. This is one question from 2010, and it is a number 6. I did it last night because I did not have the key already made up for it, and I think it is a really good one as far as you have potential to get a good score on it. I graded myself, and I got a 3.5 or a 4. You know, you can't get halves, so they decide to round up or down. The reason that I think they might have rounded my 3.5 up to a 4 is because the error I made was a small little computation. All of my statistical processes were correct. So it was a small little minor computation error. They might have considered me completely correct statistically, so they might have rounded me up. All right, so let's quiz part 1